All right, welcome to your next warm up. Now, these first questions tend to give kids problems, and it's not because they're difficult, it's actually because they're so easy, and kids are kind of like, wait, it's that simple? And yes, it's that simple. All right, so at the end of the notes last time, we started talking about density curves. And we said that the area under a density curve is always equal to 1, and that we can use that fact or use that knowledge to start calculating percentages by looking at specific area underneath the curve and saying, all right, well, if this area is 0.23 and the total area is 1, then that corresponds to 23% of the area, and so on and so forth. Now, most people, when they think of a density curve, they think of something like this, all right? They think of the normal distribution, all right? But density curves can have all sorts of shapes. So here's a curve that's horizontal from here to here, and then everywhere else, the curve is horizontal, but down here with a height of 0. All right, so there is curve here. It's just down there at a height of 0. So the first question is, what is the total area under the curve? This is a density curve, so the total area is 1. All right. You could also think of that at, well, no, we're just going to leave it at 1. The area is 1. All right. I was going to say you can think of it as 100%, but if we're talking about area, the area is 1. All right. Now it says the area under the curve corresponds to the percent of observations in that section. As such, what percent of observations are greater than 0.8? So if this is 0.8, and we know the area under the curve corresponds to the percent of observations, we're basically saying, what's this area? All right, well, that's a rectangle, right? The area of a rectangle is length times width. So we know the height is 1. We know that 0.8 to 1 is 0.2. So this would work out to be 0.2 or 20%. All right, and that's kind of what I'm saying is like, it's sometimes so easy that kids are like, wait, huh? That's all there is? Yeah, that's all there is. Now we're going to see it's not as easy to do this area when you're dealing with a curve like this than when you're dealing with a curve like this, but the concept is the same. You're finding the area underneath the curve. So what percent of observations lie between 0.25 and 0.75? So again, you're just saying, all right, here's 0.25, here's 0.75. What's the area inside of this rectangle here? Well, the height is still 1. The height of the curve hasn't changed, so the height is still 1. Only this time, 0.25 to 0.75 is 0.5. So 1 times 0.5 is just 0.5, which works out to be 50%. Okay, so really that simple. All right. Old Faithful erupts every 91 minutes. The curve below is a uniform distribution that describes this situation. If you were to arrive at a random time and wait 91 minutes, what is the probability that you would see Old Faithful erupt? All right, so again, uniform distribution is just kind of saying that it's this horizontal line type distribution. Now, if we were to wait 91 minutes, it would just be a width of 91 times the height of our curve, which is 1 over 91, which equals 1 or 100%. If we were to arrive at a random time and wait 30 minutes, what is the probability you'd see Old Faithful erupt? All right, so then our width is 30. Our height is still this 1 over 91. So you're doing 30 times 1 over 91, which is going to be about 1/3. It's not going to be exactly 1/3, but it's going to be about 1/3. It's 0.329667. All right. So you could also think of that as 32.97%. You could think of it as 33%. You could think of it as 33.0%, however you wanted to round it to which decimal place. But in each of these, the first one was a width of 91. So we were basically looking at this entire box, and we know a density curve always has an area of 1. So that's where this one came from. And then the second one said, all right, if you're there for 30 minutes, it doesn't matter whether you start here or whether you start here. If you're there for a stretch of 30 minutes, you're basically just saying, what's the area inside of that box there? All right. So a lot of times kids get confused by these because they think they have to do something more. And you will have to do something more when we move to curves like this. But for these uniform distribution curves, it's really just finding the area according to whatever situation they describe. All right, let's take a look at the back, which deals a little more with the transformations. Coach Phelps uses a thermometer to measure temperature in Celsius at 20 different locations in the school pool. An analysis of the data yields a mean of 25 degrees and a standard deviation of 2 degrees. Find the mean and standard deviation of the temperature readings in degrees Fahrenheit. All right, so we have the mean in Celsius. We have the standard deviation in Celsius. We know we're performing this calculation to every single data point that we get. So what is that going to do to our mean? What is that going to do to our standard deviation? How are those two things going to change? So this formula is really a series of transformations. All right, we've got two transformations right here. Right? One transformation is to multiply by 9/5, and the other transformation is to add 32. All right, so this goes back to the rules that we talked about in the notes last time. So adding and subtracting a constant impacts the mean, but not the standard deviation. And multiplying impacts both. So when we're questioning how our mean and how our standard deviation are going to change, for the mean, we're going to have to do both of these. All right, we're going to multiply by 9/5 and we're going to add 32. So we can do 25, or we can do 25 times 9/5 plus 32 and get a new answer of, I think, 77. Let me double check that. 9/5 plus 32. Yeah, 77. All right, so that would be our new mean. Now, our standard deviation, all right, this transformation impacts both. This one only impacts the mean. So when I'm finding my new standard deviation, I'm going to do 2 times 9/5, but I'm going to leave off the plus 32. All right, and 2 times 9/5 is 18/5, which should be 3.6. So again, this is kind of knowing these rules and knowing that multiplication and division impact both statistics, whereas addition and subtraction only impacts the mean. All right. So Clarence measures the diameter of every tennis ball in his bag. Unfortunately, Clarence doesn't know how to use a ruler, and all his measurements are 0.2 inches too long. Typical Clarence. Clarence's bad measurements yielded a mean of 3.2 inches and a standard deviation of 0.1 inches. Find the mean and standard deviation of Clarence's measurements in centimeters after they have been corrected for his incompetency. All right, so 1 inch equals 2.54 centimeters. All right, again, we are doing a series of transformations here. All right, we have to adjust for his mistake. And if all of his measurements were 2 inches too long, that essentially means we're subtracting by 0.2. All right, that will correct his mistake. And then after we subtract by 0.2, we also need to convert it to centimeters. And if 1 inch is 2.54 centimeters, that means we are multiplying by 2.54. All right. So again, going with those rules, this impacts the mean, but not the standard deviation. This one impacts both. Now, in this case, you do have to make sure you're doing them in the correct order because we're subtracting by 0.2 inches. So we don't want to convert to centimeters first and then subtract 0.2. If you're going to convert to centimeters first, then you'd also have to convert this to centimeters and then subtract it. So to make it easier, we're just going to do the subtraction first and say, okay, our mean was 3.2, but it really should have been 3. And then if we're going to convert that to centimeters, I'm going to multiply that by 2.54 and end up with, 2.54 times 3, 7.62. All right, so that would be my new mean, and that mean is now in centimeters. Now, with the standard deviation, I don't have to worry about this, all right, because adding and subtracting does not impact the standard deviation. So I can just take my starting standard deviation of 0.1. I can multiply that by the 2.54 and end up with 0.254 centimeters. Multiplying by 0.1 is just going to slide the decimal one spot to the left. Okay? But again, it's making sure that you understand that adding and subtraction only impacts the mean, multiplication and division impacts both. All right, number 5, imagine a distribution with a mean of 44 and a standard deviation of 23. Got it? All right, great. One of those observations has a z-score of 1.37. Using the z-score formula, calculate the actual value of that observation. All right, so this is something we're going to have to do a lot in the notes today. So this is just a chance to kind of think about it for a second and then see if you can come up with it. All right, so we know our formula is z equals the observation minus the mean divided by the standard deviation. And thus far, we've just been plugging in these 3 to calculate this. But as long as we have 3 of them, we can calculate any missing piece that we want. So if the z-score is 1.37, and I don't know the observation, why don't I put x in there for the observation? I know my mean is 44. I know my standard deviation is 23. And then this is just a algebra problem at this point. All right, so I would multiply both sides by 23, and that would give me 31.51 equals x minus 44. I would add 44 to both sides and get 75.5. 0.51 equals x. So this right here is my observation. All right, so again, this formula can be used to solve for any missing piece, and we are going to start using it to solve for different missing pieces. Okay, so I hope this was useful. And as always, reach out if you have any questions. All right.